Welcome ENET 140, Operational Amplifiers at Bellingham Technical College. In this lecture we'll be going over the differential amplifier. And the reason that we'll be looking at this, and in fact this is the only portion of a typical op-amp, real op-amp circuit that we'll actually be looking at in detail. We're looking at the differential amplifier because it is literally the front end to pretty much every op-amp out there on the market. And it serves a unique purpose in that it allows us to improve our signal to noise of our output signal. And we'll step through using our Kirchhoff's current and voltage laws, just like we did in semiconductors, to actually show how that happens. So I will recommend highly that you refer to the same kind of DC and AC analysis that you used in semiconductors to look at bipolar junction transistor amplifiers as we go through this treatment. And we will also pick up our good friend superposition when we look at combining the different halves of the differential amplifier and the very important effect that that has on signal, both signal output and noise output, which we're always hoping to reduce. Okay, and for this lecture I'll just be stepping through my annotated version of our Fiori textbook, our Fiori Operational Amplifiers textbook. We'll be using section 1.6, and then I'll be supplementing that with some hand notes where I focus specifically on the AC analysis of the single input differential output op-amp using all of the same Kirchhoff's voltage law analysis that we have already done back in ENET 130. Okay, so what does a differential amplifier look like? Well, here is a typical schematic, and the real heart of this is the mirror image that you can see. We have a base resistor and basically one amplifier circuit here, a current collector, transistor. This is shown with BJTs. We could make the same thing with field effect transistors. It would work the same. A little bit different biasing, but these two halves of the circuit are identical, and it's very, very important to get the performance we want from the circuit that these be identical. So the collector resistors, the transistors, especially their betas and their beta temperature responses, and our base resistors, and as we'll see, the AC base emitter resistors are all going to be the same. What's probably new for those of you who took semiconductors is instead of an emitter bias DC voltage source, we have this theoretical current, constant current source, and this is called a constant current tail when we talk about op-amps and differential amplifiers. But we can model it with just a big high impedance resistor and a voltage source, so we can analyze it the same way. Bear in mind though that this constant current source in a real differential amplifier will be its own circuit, and at the end of this chapter Mr. Fiori goes through different types of circuits that can be used for that. But we just need to remember that this is giving us a constant current through this portion of the circuit, which is known as the tail. Okay, so we're going to just go through and analyze this mirror image differential amplifier using the same procedures we would have if we'd just been looking at any kind of common emitter BJT amplifier. And I say common emitter because, as it turns out, when we do our AC analysis, we're going to take our signals out at the collectors. So effectively a diff amp is in this case is a common emitter mode. Okay, very important that we have a mirror image, that both halves of the circuit function identically. We're going to end up superimposing the output signals and canceling portions of them out and adding other portions. And so it's very important that those outputs be exactly the same in magnitude and maybe different in phase. And to get that, we have to make sure all of those components in the circuit are the same. So resistor tolerances get very important here. Resistor response to temperature, most importantly beta response to temperature, is very important. So circuit design to make the amplifier beta non-sensitive gets very important here. So we can go back to those concepts. But let's assume for now that we did all of that, that we're going to be able to treat this as an ideal amplifier let's start walking through and getting expressions for gain and for our collector currents, and then we'll superimpose an AC signal in an AC model and see what we get out of those collectors. So we'll start with our good old DC model. We've got our tail current source replaced with a large resistor and our emitter bias voltage. So this is negative, and our collector voltage, bias voltage source is positive. We have our bases at ground. So if we want to know what the current that's actually going through this RT, our tail, is, we can do a Kirchhoff's voltage law expression for this loop, and note that our base voltage is at ground, and then we will drop 0.7 volts to get to the emitter point here, which is the same voltage as this point and this point, because these are both equal. And then so we know that the voltage at this point above the tail is negative 0.7 versus ground, and then the voltage at the other end of this resistor is whatever our negative emitter bias voltage is, DC bias. So we know that the voltage drop over the tail is just the difference between those two, and we can apply Ohm's law to get the tail current. So that tail current is a combo of the emitter currents coming out of both of these BJTs. And since we have a high beta in our BJT, we know that base current is pretty small, emitter current and collector current are about the same. So if we take this tail current and we cut it in half, we have the emitter current, which is equal to the collector current, and that's what we need to get our expression for the emitter resistance for our AC model. So that's why we started with the tail current. This is going right back to what we did for small signal amplifiers. And Mr. Fiore goes through an example of how to march through that analysis with a real amplifier, and so I would suggest, if you don't remember much from your small signal amplifier studies, march through this example. It's a great review of small signal BJT DC analysis. So all of this is DC analysis. So we'll switch back to ideal, non-ideal behavior of the differential amplifier here before we dive into the very important AC analysis, where we get all of the magic. So what happens if we don't have a perfect match from one half of the circuit to another? Given how important that is, there are some cited benchmarks in your performance specs, and also that you can apply to a constructed circuit, that basically say this is how non-ideal you are. And the non-ideality or the non-symmetry of the circuit is expressed in two terms. One is called the difference in base currents, the input offset current. So if you've got different DC currents flowing into each base, that would be called the input offset current. And if that results in a difference in collector voltages, that's expressed as the output offset voltage. So that's kind of your real state. Those are never going to be zero. You'd like them to be. You can drive them to zero by applying a base voltage that results in no difference between the two collector outputs, and that is known as the input offset voltage. So if you have to apply, say, I don't know, 100 millivolts, say, to one base to get the same voltage output at the collector, you would say 100 millivolts is your input offset voltage. So that's what you had to do to make the two halves of the circuit behave the same from a DC standpoint. So these are numbers that you'll see published for a given differential amplifier circuit. So it isn't just a function of the transistors themselves, it's the as-built circuit. So a little bit of vocabulary there and why it's important. Okay, so let's get into our AC analysis. And for this, unfortunately, Mr. Fiore kind of broke his rules. He's not expressing, or he's not modeling, excuse me, his BJTs the way we would probably want to see. He's leaving the schematic. These should really be those AC current sources right here, because a good AC model of a BJT would just be an AC current source in the direction of conventional current flow instead of the schematic symbol, but he's kind of left the schematics in. What's important from our standpoint is our emitter resistor, our little RE, that we needed our collector DC current to get. Remember, using our Q point to evaluate this using our diode equation. So that's why we started with our DC model. But one thing we can look at with the circuit drawn this way with our signal inputs is we can notice we got a lot of choices. If we just had a single BJT and a small signal amplifier, we could put a signal in one place and we could get a signal out another place. Here we can put a signal into the base of transistor 1 and get a signal out of transistor 1 or transistor 2, or we can subtract the two and take the difference. We can take that signal away and we can put a signal in the other transistor and then get an output at either V out 2 or V out 1 or the difference. And one of the nicest things about these types of circuits is, in spite of the fact that they are not just resistors, normally we wouldn't use superposition or wouldn't assume we can use superposition with semiconductor components. These are. The way the circuits are built, at least for AC, we can use superposition to look at the difference in the effects of this voltage signal, this voltage signal, and the results on the output. So this makes our analysis way easier. We can put a signal in one place, look at the outputs, and then take that signal away, put the other one in, look at the effects on the outputs, and just add them. Just add them up. So just like we did with Ohm's law in our DC circuits, we can use that same kind of superposition for the differential amplifier, because the as-built circuit turns out to be linear over the range of voltages, amplitudes that we'll be using for signals. And that brings me to just a general rule, especially for those of you who might be going on to classical engineering studies. Things tend to be linear when they're small. And this is something you may have used if you studied calculus when you looked at deriving the equations for derivatives for different functions. If you take very, very small steps, even a very nonlinear function can look linear over a little tiny increment. And that's the same kind of principle that's allowing us to use superposition, even though obviously we have semiconductors where current voltage relationships are anything but linear. We're using very small signals and we're using ranges where that assumption is approximately true. So that makes our life really good, because that allows us to do a lot of very creative things with our output and cancel out all that noise. So just to get you thinking, I'll refer to this figure 121, which just kind of steps through all the different ways you can hook these up. So you can put a signal in at both bases, so dual input, and you can look at a differential output, just subtract the two outputs. I can put a signal in just one place, and then I can take the output as the difference in the two collector voltages. I can put signals in at both places and only take it out at one or the other, and I can put it in at one place and take it out at one place. So these all have different names: differential input output, single-ended input output, and all the ways in between. Okay, so having done the big run-up, let's look at a simplest case. Let's look at single-ended input, and let's look at our AC model here. So here's our input signal, V in, coming in with our little waveform generator right here. And so we're going to apply it to the base of the transistor, and we're going to potentially take signals out V out 1 and V out 2 at our collectors. So we're common emitter, so we're taking signals out at the collectors, V out 2. A little bit messy, but we know where our collector potentials are. They're right at the collector end of the BJT. Okay, so essential features of our AC model. We now have our emitter output resistance, our R little e. that we used our collector current and our 26 millivolt ratio to get. And important, we're going to assume that this tail resistor is huge. So it's going to act like an open. So really, that part of the circuit just kind of goes away. And our emitter currents, our collector current is going to flow for our circuit 1 is going to flow from ground and drop over the collector. So Vout1 is going to be less than ground. So it's going to be an inverted signal, which we're used to from common emitter. So our emitter current coming out of our first BJT is going to flow through RE1. It can't go through RT because we're going to assume that's so big it might as well be an open, and it's going to flow through RE2, and then we're going to refer to a different AC circuit schematic to see what happens after that, because this one doesn't show it too clearly. But before we skip to that, we'll just focus on our collector currents and voltages. We know from our AC model, we can say we've basically eliminated our DC voltage sources and grounded them out like we always would for our AC model. So we can write an expression for our voltage drop over the collector resistor as just the collector current times the RC1, and the same with RC2. And we can assume that our collector AC current and our emitter are approximately the same, just like we do with DC, because we can do that with a BJT for both modes. Okay. At this point, I am going to skip to an alternative schematic, which you have available to you. I'm going to pull it off my hard drive, but it's available to you right in your module, and it's the hand note version of this same presentation in the book. So here I'm over at my hand notes now, and I am looking at the single input differential output, same differential amplifier, and here's my AC model that I've drawn using those classical current sources and emitter resistors that we learned back in ENET 130 in semiconductors. So, but it's the same circuit. So we can go and look at, here's our input signal, single-ended input going into transistor 1. We have our AC current source, which we're representing the transistor as. So here's our collector current 1 flowing from ground over our collector resistor. So our collector point 1, collector voltage 1, this is going to be one of our outputs. Remember that a current source has huge impedance, so nothing's going to flow back up through it. And so our emitter current's going to flow down out of the transistor. It's going to flow over RE1 and drop some voltage to this point E1. It's going to drop more voltage over our emitter bias resistor, the one that's external to the BJT. This isn't open because RT is huge. So that same IE1 is going to flow, and it's going to continue to flow through the bias resistor, emitter resistor of the second amplifier, and we're going to get to E2. It's going to flow through the emitter output resistor of the second transistor, and then it can flow to ground. So we could write an expression for the voltage at E1 or at the base. We're going to apply Kirchhoff's voltage law of ground minus that first circuit emitter current, voltage drop over RE2, little RE2, big RE2, big RE1, and little RE1. So we've got current flowing out of our first transistor over those 4 resistors and to ground here at our second. That's our path to ground. It can't get to ground through the tail, so it's going to flow to ground through the base of the second transistor. There's the path, just Kirchhoff's voltage law. So, and this is our base resistor. And we know that that emitter current is approximately the same as the collector current. Now, here's the trick. If you take either of these nodes, E1 or E2, but especially focus on E2, remember that we have current flowing the other way through the other transistor. And we can go through the same argument looking at its magnitude and the voltage at our collector 2 on our second transistor, and we're assuming these are all identical. All of these R's are the same and our betas are the same. So we actually have an IE2 flowing in this direction. And it's not going to flow to ground because it's already below ground. It came from ground and it dropped over this resistor. Now the current source of the transistor, the power supply of the transistor, is giving, keeping it going, and it's going to flow into this node. Now we know that from Kirchhoff's current law, the current entering and exiting this node have to be the same because there's nowhere else for it to go. It's not a three-way branch, it's just got two branches. So that tells us that IE2 and IE1 have to be equal in magnitude and opposite in direction. Well, what does opposite in direction mean to AC? It's always going in two directions, right? It's AC. It means it's at a phase. So we know that the current, both the collector and the emitter current in our second amplifier circuit is equal in magnitude and 180 degrees at a phase from what's going on over at the circuit where we're putting in our input. And that's an essential part of how these work. And we can say that IE1 and IE2 are equal in magnitude and 180 degrees out of phase by just applying Kirchhoff's current law to one of these nodes when we draw our AC circuit. So if we put that fact together and then just go through our Kirchhoff's voltage law analysis for AC and apply it to both sides of the circuit, we get these really important relationships for our emitter currents and our voltage outputs, which are going to give us our gains for both sides of the circuit. So let's just go back and refresh on our transistor 1. So our V output 1 is going to be the collector voltage right here, because this is common emitter, so we take our voltage output there, and it's going to be negative collector current times our collector bias resistor, because we go from ground and we drop over that. So that's a negative. We can write the voltage at our base, this point right here, base 1, using a KVL along this loop, this long current path. So we can say the voltage at this point is ground plus whatever we dropped over each one of these four resistors, and we dropped it by flowing our emitter 1 AC current through it. And we're going to simplify by saying, because we got a mirror image circuit, our little RE1 is the same as little RE2, big RE1 is the same as big RE2. So we can just factor out a 2, and we can get this expression for our IE1 in terms of V input. Because, oh yeah, this is common emitter, so my input is the same as my base voltage right here. They're just connected by a wire. Great. Now I have a way to express my output in terms of my input, because I know that IC1 is about the same as IE1 because it's a BJT with a big beta. So now the only thing I need to do is look at what's going on in the other half of the circuit. So I can use the same kind of analysis. I can say, okay, my output voltage or my collector 2 voltage is just going to be ground minus the collector current flowing over RC2. So here's this expression. RC2 is the same as V out 2. And I can write an expression for the voltage at the second emitter in terms of the base and ground. So I can do, let me erase a little bit of this previous loop. And you'll notice that we're treating our second amplifier circuit about like a common base. So even when you put it together with its pair, they're both in common emitter mode, we can look at it as a common base configuration. And that makes it easier for us to do this analysis. So that's why this is dotted line with treated as a common base. So that allows us to make a little KVL loop right here to get an expression for the voltage at this E2 point. So we go from ground at 0. So B2 is at 0. It's a ground. So we will drop a voltage to get to E2 equal to IE2 flowing over RE2. So we've neglected the input of the effect of the current from the first transistor for this expression because we're going to use superposition. So over on this side we're only looking at the effect of the current flow from transistor 2. Okay, so this is same expression in the dotted area, just reminding us of the relationship between IC2 and IE2 drawn here as a common base. Okay, so now we can relate IE2 and IE1 and go back over and say, okay, I want an expression that's only written in terms of either IE1 or IE2, because I can't solve for two things. I don't want two variables. That'll make it impossible for me to solve. So I want an expression for VC2 or Vout2 because that's my second output. And I want it in terms of just the emitter current of transistor circuit 1. So here's where I use my same magnitude 180 degrees out of phase expression for our two emitter currents. And I plug it in over here. So I can go from this expression all the way down to here with some math. So I use two relationships. Collector current and emitter current are the same approximately for a BJT, and because of our differential circuit configuration, IE1 and IE2 are same magnitude, opposite direction. So I just plug that in. And now I have an expression for Vout2 in terms of collector current 1, and I can use that in combo with this expression for input versus collector current 1. And I can come out with expressions for output voltage in terms of input voltage and my collector currents, my collector resistors and emitter resistors in both cases. Boom. Lots of red circles here. The double arrows are important because it's showing that our outputs at both 1 and 2 are the same, Vn, Vn. The two collector resistors, which should be the same, are AC little emitter resistors and our big biasing resistors. All of this is the same except for the direction. So I would advise you step through the math. It's really easy algebra. We can get an expression for Vout 1 and 2 that are opposite in phase but the same magnitude. So that's the big takeaway. And now we'll flip back to our annotated notes. So that's the real magic of the differential amplifier is our gain or our output signals are going to be opposite in phase for a single input. So here's the way the waveforms kind of pan out. We'll just skip ahead to figure 124. So if this is my input signal that I put in, the output at collector 1 is going to be out of phase with that input, and the output at collector 2 is in phase with the input and completely out of phase with the other output. So we can either, if we subtracted VC1 and VC2, they would cancel out. If we added them. If we subtracted them, they would double. So we can get very, very different outputs depending on whether we add or subtract or we just take one or the other. So that starts to form the basis of all the great things we can do with the differential amplifier, because we can combine different inputs one output or the other output, knowing that we can look at corner of the box relationships in terms of our inputs being identical but out of phase and our outputs being identical but out of phase, and which ones do we want to take. So I'm not going to step through every one of these nuances, but I'll just refer you to the textbook where Mr. Fiore goes through these two corners of the box of two identical inputs in phase and the same magnitude, and two inputs of identical magnitude but out of phase. These represent the corners of the box of noise in the first case and a signal that we want to amplify in the second case. So we'll just step through those. So we're going to start with what's known as common mode. So we're going to put an input signal in on amplifier 1 and on amplifier 2. They're the same magnitude and they're in phase. So that's represented by these two inputs. So the collector output at collector 1 as a result of this input is going to be out of phase, and collector 2 it's going to be in phase, just like we saw with our single input derivation we just did. And we've got the opposite for the collector output voltages due to the second input because they are reversed. If we combine these collector outputs due to both inputs, they cancel. So if I have common mode inputs, so I got the same magnitude and in phase, that's what common mode means, same magnitude, same phase, coming in on both inputs, and I combine the outputs at the outputs due to both the input signals, they completely cancel. Here's the reason this is important and why differential amplifiers are used as a front end for all of our op amps. Noise tends to be common mode. It tends to be in phase across a wide range of frequencies, and it has the same amplitude as itself. Our signals we can manipulate and bring them in on both sides of the amplifier out of phase deliberately. We can't manipulate noise that way, but the differential amplifier allows us to cancel it out naturally just by combining the signals at our output. And just to make ourselves sure, we can, this is differential mode. We can, if we have two signals that are out of phase, so we're going to put an input in on transistor 1, Q1, and we're going to put out of phase input on transistor 2. See the two inputs here. This is out of phase with each other here. You can see the sine wave is completely out of phase, 180 degrees. These are individual outputs, and when we combine them, look, we get 2V. So rather than canceling, they double. They're additive, which is exactly what we want for a signal. And the ability of a differential amplifier to cancel out common mode signals but to amplify differential signals is known as common mode rejection, and it is a performance benchmark of the amplifier. And so Mr. Fiore discusses that here. So that's probably one of the most important performance benchmarks that you'll pick when you're using a differential amplifier for a noise sensitive circuit or someplace you need high signal to noise. So that is it for our differential amplifier lecture. If you really want to see the magic of how these work, I would highly advise you step through your AC model, Kirchhoff's voltage law expressions for those simple circuits with the single-ended input, and then use superposition and combine. You can do that all mathematically if you want. You can also just remember in phase cancels, in phase inputs cancel, out of phase inputs are additive when we're taking them out at both sides. But either way, we use all the same properties of our BJT or FET amplifier circuits that we learned in semiconductors, and now we just apply them working together with that mirror image. So You will have some exercises that you can use this, and then we'll move forward into Chapter 2 and just remember that this is the front end of all of our amplifiers, and we'll follow through some of Mr. Fiore's discussions on the middle stages where we get all the gain, and then the output where we're going to use Class B amplifiers to make sure all of that power gets conveyed out of the circuit. So stay tuned.